Welcome back, everyone. As always, make sure to subscribe to my channel in order to see more chemistry videos. And make sure to check out the electron arrangements video. Link is in the description below to catch yourself up on valence electrons. So the purpose of this video is to introduce electron dot structures or Lewis dot structures. Now, before we talked about how valence electrons are electrons in the outermost shell of an atom and how important these are for your chemical properties. And they can be determined by the group number for the main group elements. So a Lewis dot structure is a quick representation of the valence electrons for each atom, and those valence electrons are going to be represented as dots. So, with the examples here on the right, the important thing is that when we are putting the dots around the atoms, that we're very systematic. So we want to only represent dots as a single electron or as a single dot until we get up to 5 electrons. And we're going to use the top, bottom, left, and right to put an electron on each side. Lithium, if you notice, we're starting by putting an electron on the right side. Now you could have chose the top, bottom, or left, and it would have been okay. But once we select that right side, when we add the second electron for beryllium, which has 2, we continue to add the electron that's on the right, and the second electron we're going to put across on the left. Okay? When we get up to 3 electrons, again, we don't want to put that third electron on the left or the right side because those are occupied already. So that third electron we're going to choose to put on top. And again, you could have chose to put it on bottom, that's okay. And then at that point, when we get up to 4 electrons, well, the top and the left and the right sides have been taken up. So that 4th electron is going to go underneath on carbon. Okay, once we've used up all 4 spaces, top, bottom, left, and right, then we can start to group those electrons together. So when we get to nitrogen, which has 5 valence electrons, that 5th electron can be paired with any of the previous 4. And here they've decided to put it on the right-hand side. Okay, going up to oxygen, which has 6 valence electrons, we're going to have to create a second pair. Okay, so you only ever want to have a maximum of 2 electrons grouped together. And so that 6th electron we will pair on the left-hand side. Fluorine has 7, so then we will add a third pair on the bottom, and neon has a total of 8 valence electrons, and so that 8th electron will be paired on top. Okay, so again, just very important that you add them as single electrons until you get up to 5, at which point that you can start creating pairs of electrons. Now these Lewis dot structures, again, keep in mind that they do connect back to the periodic table. So if we remember the groups 1A, 2A, and skipping those transition metals, the main groups pick back up at boron with 3A, carbon 4A, and then all the way up to the noble gases, the last column is 8A. And so those numbers represent the number of valence electrons, and they also represent the number of dots in your Lewis dot structure. Carbon as an example here, we have 4 dots, 4 electrons, and it is in group 4A. Now, the purpose of these Lewis dot structures is so that we can eventually start creating what we call covalent bonds. And covalent bonds, remember that those are going to be bonds between 2 or more nonmetals. Remember that when we dealt with bonds between metals and nonmetals, those were considered ionic bonds. So in this case, we're looking at all nonmetals, and those will create your covalent bonds. And the first type that we're going to look at is a single covalent bond. And a single covalent bond is going to be formed by two electrons that are shared between two elements. And the simplest example is a hydrogen atom. So a hydrogen atom, remember that it's in group 1A. So it only has one valence electron. And remember that hydrogen is considered a non-metal. So if we take two hydrogen atoms that each have one valence electron, they can form a bond by sharing these two electrons. Okay, and you may see it sometimes represented as two dots vertically placed between the hydrogens, but more often you're going to see it represented as a line between those two hydrogens, okay? And that line represents a covalent bond which contains two electrons. Now we can determine the number of covalent bonds that each element will form based on its Lewis dot structure. And every single dot that you see can form a covalent bond. And remember, I said a single dot. So carbon has 4 single dots around it, and therefore it can form 4 covalent bonds. Okay, so we can use hydrogen as an example. We can place a hydrogen on top, bottom, left, and right around that carbon. And so it will form a total of 4 covalent bonds. And I'm just abbreviating here. Now, nitrogen only has 3 single electrons. It's got one on top, on the left, and on the right. We cannot bond the 2 that are already paired together because they already have 2 on that side. So nitrogen will form 3 covalent bonds. Oxygen only has 2 single electrons, and therefore it will form 2 covalent bonds. Fluorine has 1, and therefore 1 covalent bond. And our noble gases, represented by neon here, all 4 sides have pairs of electrons, and so therefore there will not be any covalent bonds to neon. Okay, so if you notice, again, this is as we're going across the periodic table. So if we look at the periodic table, carbon is in group 4A, and it forms 4 covalent bonds. And that's true for carbon and silicon below it. Nitrogen formed 3 covalent bonds, and so nitrogen, phosphorus, and sometimes even arsenic, those will all form 3 covalent bonds. So remember, this was 4 bonds. Nitrogen was 3 bonds. Oxygen, sulfur, and selenium, those will form 2 bonds. And then your halogens, 1 bond. Okay, again, because the valence electrons or the electron dot structures are similar in each group. Now, notice how for nitrogen, it had that pair of electrons and we didn't bond it with anything. So when you have a pair of electrons that are already together on an atom, we call those lone pair electrons. And they're going to be represented by 2 electron dots that are grouped together in the dot structure. And so carbon, notice how it doesn't have any lone pairs. And I'm going to abbreviate lone pairs in the future as LP. Okay, so carbon has 0 lone pairs because all 4 of its valence electrons are singly placed on top, bottom, left, and right. Nitrogen has 1 pair. Oxygen, 2 pairs. Fluorine, 3 pairs. And neon, 4 pairs. Okay, so this is why it's very important that you do not start grouping those electrons too early until you have 4 single electrons, and then by the 5th you start making groups, because that helps you determine how many covalent bonds that you have and how many lone pair electrons that you're going to have on each type of atom. So to summarize, groups 1 and 3A are a little bit of an exception to the rules typically, but in group 1A, the only element we worry about for covalent bonds is hydrogen, and it will have 1 covalent bond and 0 lone pairs. And then boron in group 3A, represented by B, will have 3 covalent bonds and 0 lone pairs. Now after that, there starts to become a pattern. So in group 4A for carbon and silicon, you have 4 covalent bonds and 0 lone pairs. And from there, the number of covalent bonds is going to decrease while the number of lone pairs increases as we go across. So 5A would be 3 covalent bonds, 1 lone pair, and then 2 and 2 for 6A, and 1 and 3 for 7A. And if we were to include the noble gases at the bottom, those are going to have 0 covalent bonds and 4 lone pairs. And the reason we don't tend to include those is because they're not going to form covalent bonds, so we don't worry about them too much in our Lewis structures. Okay, the last topic for this video are molecular formulas. So we looked at molecular formulas when we looked at balancing chemical equations. And molecular formulas are just a concise list of elements in a compound with the ratios of these elements represented by the subscripts. So when you see a subscript, that tells you the number of atoms that you have of each element. And the Lewis structures, which we'll get into more detail, but they are used to represent the bonds between those atoms. And so if we look at a Lewis structure, we notice that we have 1 phosphorus in this Lewis structure, and we have 3 chlorine atoms. Okay, so those 3 chlorine atoms are represented in the molecular formula with the subscript 3. And then phosphorus, because it's 1, that's assumed. And when it comes to ordering the elements in the formula, in this case, if there's no carbons or hydrogens, typically you're going to start with the central atom. So let's include this rule that typically you start with the central atom. And the central atom being the one that's in the middle of the structure, okay, which is phosphorus in this example. But more often than not, we're going to have a bunch of carbons and hydrogens and possibly some other elements. And when that's the case, carbon tends to be the central atom. And we go in the order of carbon, then hydrogen, and then the remaining in alphabetical order. So let's look at some quick examples. Hopefully this part's pretty easy. We're just going to count up the number that we have of each type of atom and list them in the order of carbon, hydrogen, and then everything else. So in our first structure, we have a total of 3 carbon atoms. So that will be 3 with a C with a subscript of 3. And then we have nothing left but hydrogens. Okay, so we're going to count up the number of hydrogens. We have 3 on top, 3 on the bottom, and then 1 on each side. So 3 plus 3 plus 2 gives us a total of 8. And so our molecular formula for that first structure is C3H8. The second example, again, we have 3 carbons. So that's a C3. And then 1, 2, 3, 4 hydrogens. So C3H4. Okay, in the next structure, again, remember to start with the carbons and hydrogens first. So we have 1 carbon, and since it's 1, we don't show the 1. H2, and last we have O. Okay, and then in the last example, we have 2 carbons, 5 hydrogens, and 1 chlorine.